Hello and welcome back to CG 101, and today we're going to go in depth into the subject of chemical engineering calculations, also known as CHECALC. And specifically, we're going to be going in depth into the topic of the atomic balancing method. And today you're going to be joined by me, Kit Ivan Kalakday. To start off, we have our outline for today. First, we'll start with our problem statement. And then follow up, we're going to talk about the theories that are applicable for this current problem, specifically the conservation of mass and the atomic balance method. Then we shall continue with our solution, both the generalized idea as well as our step-by-step process in how to solve the problem. And then we shall end today with a summary of what we did today. Now for our problem statement. A reaction occurs in a reactor between two input streams, one containing silver nitrate and another contains copper and inert material. The reaction that occurs is shown below. Silver nitrate reacts with copper, resulting in silver and copper nitrate. If the reaction required 50 kilograms of copper when processing the silver nitrate, and the total amount of material within the whole system is 350 kilograms, how many kilograms of each material was in the system before and after the reaction? And also listed here, we have the molar masses, specifically in grams per mole, kilograms per kilomole, what have you, for all of the materials inside the system. As for our theories that are applicable for today, we have the law of conservation of mass. It states here that the matter cannot be created nor destroyed in whenever. So, matter is constant for our application. Matter is constant throughout the entire system. Both the amount of mass before the reaction starts and the amount of mass after the reaction happens must be constant. Secondly, we have the atomic balance method. It is a method that is used to solve the process within the chemical reaction, specifically how much of a certain material turns into another material. And this is through the use of equating the moles of one element to another element within the same system, just in a different compound. For example, you will see this applied later within our testing, and we shall see it in just a moment. As for our solution, we see here that we are given both the mass of copper as well as the total mass that is present within the entire system. And we need to find the mass of silver nitrate, silver, copper nitrate, and the inert material. As for our solutions that we are going to use, first we are given the amount of copper, the mass of copper within our system, but we need to turn this into the moles of copper within our system. And since we know that these moles of copper start out in our system, specifically in the reactants, and we know that the moles of copper in our reactants must then equate to the moles of copper inside the products. And since we know that this is the amount of moles of copper inside our products, we can then turn this into, since there's only one form of copper inside the product, specifically, it's copper nitrate. This is in moles. And then from there, we already have one of our necessary by turning this into mass, while we can then turn this copper nitrate into the moles of nitrate inside our product. And since we have our moles of nitrate in product, we can then turn this into our moles of nitrate inside the reactant. And then we can apply this once again to turn our moles of nitrate inside our product, inside our reactant, into our moles of silver nitrate. And from our moles of silver nitrate, we can get both the mass of silver nitrate, or and also the amount of the moles of silver inside our system. Then since this is in our reactant, we now also can get moles of silver inside product. And then from there, we can then get moles of silver product. And since that's how it is present inside our product, just turn this to mass. Now we have obtained three of our four necessary things: mass of copper nitrate, mass of silver nitrate, and also the mass of silver. Now, how do we solve for the inert? Now, we mentioned earlier about the law of conservation of matter. So then that means that the matter inside the whole system must be constant. So mass total must be equal to mass of all components which is either mass of all reactant or mass of all product. Next, so time to start our main solution. First, we are given the system, since this is always necessary whenever starting an equation. So we have two input streams. I shall label them A and B. And since the system never mentioned, we shall label one exit stream as C. So for A, we have silver nitrate, so AgNO3. Oops. Our second input stream has copper and inert material. And then as for our exit stream, we have copper nitrate, inert material, as well as silver. First, we are given the mass of copper if at the end, not at the start. So we know the mass of copper in B. That means copper in B is equal to 50 kilograms. But we have to convert this into moles. So it was given at the start of the problem statement that it is 63.546 grams per 1 mole. This is also, you can turn the grams into kilograms, but you have to turn the moles into kilomoles. So we shall get, if you were to graph out your calculators, 50 divided by 63.546. You will then get I shall simplify this, 0.78683 kmol of copper. Using this information, we know that since we have 0.78683 kilomoles of copper at the start of your thing, so 0.78683 kmol copper reactants, which must be equal to k-mole copper in product. So since we know now that there is 0.78683 k-moles of copper in your product, you then have this would then, since in our reaction specifically, we have in our products specifically of our reactor, it's all so copper is only present in one form, which is copper nitrate. And if we look at the formula, CuNO3 2. That means there's only 1 mole of copper per mole of copper nitrate. So that would mean we have 0.78683 k-mole of copper nitrate. Now, to make use of better of our atomic balancing method does not follow molecular balance method, specifically in trying to equalize the amount of moles. In atomic balancing method, the number that you're trying to solve, that you're basing your multiplication, for example, if it has to be times 2 or times 3, is completely based on this small number right here. The amount of moles of a certain component in the entire compound. So, for example, especially in this equation, we were not actually given the balanced chemical equation of the entire system, and yet we can still solve for each of the components, like here. So we know that per mole of copper or nitrate, there are 2 moles of nitrate. So that means you have to get this original value of 0.78683. You then have to times this by 2. For per mole of copper nitrate, we have 2 moles of nitrate, which then results you into the moles of nitrate you have in your system, your kilomoles of nitrate in your system, which would then result into 1.57336 kmol of nitrates in your products. From here, you can then solve for your amount of kmoles of nitrate in your reactants, which is going to be equal to the initial value, which is 1.57336 moles of nitrate in your inside your products, which is then equal to k-mole of nitrate in your reactants. And then from there, since you have that amount of kilomoles of nitrate in your reactants, so we have 1.57336. We then have to relate that to our nitrates inside our reactants. And for this situation, we have only 1 mole of nitrates per mole of silver nitrate. So then we have to times it by 1, technically. That's 1 over 1, but in this case we shall simplify to 1. And as well as cancelling out other elements such as your kilomole nitrates into kilomoles of silver nitrates. So then we shall result into 1.57336 kilomoles of silver nitrate. This is your kilomoles of silver nitrate inside your reactant. So now we know also. So far we know what's in A. This was given, and we know what this is. Now the only one that we can currently solve for is for silver. Repeat the process again, but now since there's only 1 mole of silver per mole of silver nitrate, which is equal to 1.57336 moles of silver. And then repeat this once again. Whatever's in your product is in your reactant. That means you're gonna have 1.57336 mole of silver reactant, which is equal to, oops, not silver, it's K mole. Oops, excuse me. Okay. So this is now equal to 1.57336 K mole silver in product. And since silver appears only once in your product and it's naturally shown as silver, we already have your last value for moles. So for the next part of our solution, we have, we are given so now we have, oops, excuse me. So we're given 0.78683 of copper nitrate. Wait first. We are then given 1.57336 moles of silver nitrate and 1.57336 K moles of silver. Now our next option is to solve for the masses of each of these materials. So we know first and foremost in our system that we have 0.78683 of copper nitrates. We have 1.57336 of silver nitrate, as well as 1.57336 silver. If we were to convert all of these into mass using the conversion factors earlier, note these are all in kilomoles, so that means you're going to result with an answer with kilomoles. It shall result you into, here. So you have 1.57336 with 169.87 for silver nitrate, resulting you with 267.27, 267.27 kilograms for here. For your copper nitrates, it's 0.78683 times here 187.56. You shall result with 147.58 kilograms of copper nitrate, and for here it's 1.57336 times that by our initial value, by the conversion factor, which is 107.87. It shall result you with 169.72 kilograms of silver. Just to check again. Oops. These are using the correct conversion factors. These are all in kilomoles, and you should then result into kilograms. 147.58, 269.27, and 169.72. Now, with all of these said, you know, using the law of conservation of mass, that mass in your system shall always be constant, and you know that you started with 350. So you could use either your products or reactants. So let's say in this situation, let's use your product. Let's use your reactants as an example because one of them was already given. We know that we start with 350 kilograms, which must equate to mass of your which must equate to your mass of copper, which is 50 kilograms. You add that with their mass of your silver nitrate, which is 269.27 kilograms, and add that with your kilograms of inert material. And if you were to do some basic algebra, which is 350 minus 50 minus 269.27, you shall then result with 30.73 kilograms of inert material. And so, with this in mind, we now know all of our materials here. And as a way to check, you could add all of them up to see if it really equates to 0. Note that if there is some slight differences amongst the numbers, wait, 69.87, 0.7683 times 169.87, yes, wait, is that right? 169.87, 0.78683. It should result with, excuse me, that is the wrong material. 187, I see. So it should result with all these three values, and as a way to check, even with a slight difference due to rounding errors, 147.58 plus 169.72 plus 30.73, because inert material must stay constant throughout the entire situation because it reacts with nothing. You should result into a value that is relatively similar to 350 kilograms. If you were to add this value, and not that, this value, and this value, it should result into something somewhat similar to 350 kilograms. Note there are some errors due to rounding earlier, or like using simplified values instead of using the whole value in your calculator, but it should result into something similar. And as for a complete solution, as for proof, we now have 50 kilograms, convert that into kilomoles. From those kilomoles of copper, you could then turn that into your kilomoles of copper nitrate, and then from kilomoles of copper nitrate, you have to times it by 2 because there are 2 moles of nitrate per mole of copper nitrate, and then use that to solve for silver nitrate, and then from silver nitrate you can use that to solve for silver. And then from there, you can add oops, I must have inputted something wrong, excuse me. That should be 32. So 300, so that's 350 minus 50 minus 269.27. Well, it's 267, I wrote it wrong, excuse me. This should be a 7. I wrote it wrong. This is 32.73, which is why the answer was somewhat odd earlier. But anyways, we now know this, that the inert material is equal to 332.73 We know that the mass of your silver was 169.72, silver nitrate 267.27, and for your copper 147.58. And with that, we have now gotten all of our solutions correct. And as a way to wrap up our discussion today, we will now talk about our summary. Atomic balance is used to predict outcomes for chemical equations. The most of a specific element is constant throughout the system, as well as mass cannot be created or destroyed, and as such is always constant within the system. Remember, when using the atomic balancing method, you do not need the the uh, molar ratios to solve for it, given that in our original equation we never actually used any molar ratios for solving it because the original equation was unbalanced. All you need is the description of all of the molecular the molecular formulas for the compounds. Specifically, how many moles of a certain element is inside this one specific compound. And as such, that should be it for today's discussion. If you have any questions, email chen.acads@gmail.com or visit us at facebook.com/chen.acads-hub. And thank you very much for today's discussion, and I will see you guys next time.